All right, class, we have just two more Marin factors left to discuss, and the first of those is reliability. Fatigue is a stochastic phenomenon, so even if you have test samples that appear identical, they're going to have different endurance limits. The endurance limit of a rotating beam specimen is typically reported to you at a 50% reliability level. That means that if we say that the endurance limit, SE prime, is 75 KSI, for instance, about 50% of specimens are going to have a higher endurance limit than that, and 50% will have a lower endurance limit. So if you want to design your parts, the real parts, with a reliability that's better than the 50%, you need to knock that endurance limit down by a reliability factor so that a greater percentage of parts that you make are going to have an endurance limit that's higher. And this here is going to be a plot of the reliability factor as a function of the reliability that you want. So here we have the reliability percentage on a sort of logarithmic scale approaching 1.0 or 100%. And the reliability factor is given on the vertical axis. And this is what the plot looks like. At a reliability of 50%, the reliability factor is 1. You don't have to reduce the endurance limit if all you need is a reliability of 50%. If, on the other hand, you need a 99.9% reliability for your parts, you're going to have to knock down the endurance limit that you have by a factor of about 0.75. So these factors are listed in table 6-5. I produced this curve as a handy reference, but if you need more precise values for standard levels of reliability, then you can look at the table. And finally, we have a miscellaneous effects factor. This is everything else. These values are not always available for every possible thing that could affect the endurance limit of parts, but nonetheless, you should consider whether there are any residual stresses, like we talked about with W sections. They can end up with stresses, even the absence of load inside, and that can affect fatigue. If they're tensile, or where they're tensile, that's going to increase the chance of fatigue. Where they're compressive, that's actually going to tend to reduce the chance of fatigue. Directional characteristics. Some kinds of materials have different properties in different directions. You need to consider that. Surface treatments that the parts might have, whether they're coated with zinc or some metallic coating that might be sprayed on, those can introduce cracks. Corrosion. We're talking about steels for the most part, and steel corrodes if it's not protected. And that can absolutely increase that can definitely lower your endurance limit. In fact, if it continues to corrode over time, you're not going to have any endurance limit because eventually the part's going to just rust all the way through, right? And finally, frettage, when there are parts that are mating tightly, like bolted joints or bearing fits, the parts can rub against each other and that can wear away at the surface and cause micro cracks that will reduce your fatigue strength. So all these things need to be considered, and some of them Shigley gives factors for. I suggest reading that section of the chapter in Shigley. We're on the endurance limit modifying factors section, and we're talking about miscellaneous effects factor. Take a look at that, and you'll find some factors mentioned there that could be useful. Let's do an example. We have a polished steel specimen that has an ultimate tensile strength of 250 KSI. And other than a few things, it is just a normal rotating beam specimen. It's going to undergo a rotating beam fatigue test, but it has a sprayed metallic coating. And we also want to estimate the endurance limit with a reliability of 99.9%. Okay, so the two things that we know are that we have a metallic coating, sprayed metallic coating, and we want the reliability to be 99.9%. If we wanted to find out the endurance limit, we're going to take our reliability factors that we're going to have from these things. We're going to have a KE and a KF. KE for the reliability and KF for this miscellaneous effect. And we're going to multiply those by SE prime, the endurance limit of a perfect specimen. So let's start out by finding SE prime. Well, we have an SUT, ultimate tensile strength, of 250 KSI. And we say that normally we say that 0.5 times SUT would be our endurance limit of a specimen. But this is only when SUT is less than or equal to 200 KSI. When SUT is greater than 200 KSI, we just have 100 KSI. That's the recommendation Shigley makes, and so our SE prime in our case is just 100 KSI, not 125 KSI. Let's find our factors. So KE, the reliability factor associated with a 99.9% reliability, is 0.753. Easy. You know the reliability you need, you just look it up in the table. And now KF, well, we have to take a look at the chapter in Shigley. And it turns out that you'll find this in the chapter. Metal spraying results in surface imperfections that can initiate cracks, and there are some tests that show a 14% reduction in the fatigue strength. 14% reduction means KF is equal to 1 minus 14% is equal to 86%, or 0.86. And so we can find the endurance limit of our actual specimen, the 99.9% reliability level, by multiplying by these factors, 0.753 times 0.86 times 100 KSI. And we have an endurance limit of 64.758 KSI.